I'm pleased to be here today, and I wish to thank Francesco Iacoviello and Alexander Sedmak for inviting me. It's exciting that we're going to have a virtual ECF conference. So today I would like to talk to you about delamination failure, which is something that my group has been working on for quite a number of years. And my coworkers are quite extensive. I've had many PhD and MSc students. Some of them are working at the moment, and I've had two engineers with me, Rami Eliassi and Victor Foreman, for the last 25 years, who have been working diligently to help the students to carry out the experiments and to do the numerical studies. So we are motivated here to talk about the use of composite materials and laminates, which continues to increase. And here we see on the left-hand side of the slide, we see the rear fuselage of an Airbus 350, which is made of laminates. And then, not to be outdone, Boeing in their 787 Dreamliner also has a laminate fuselage. And in both cases, composites consist of 50% by weight of the material in the aircraft structure. So certainly composites play a large role in modern aircraft. There are problems with laminates. And first of all, what is a laminate? A laminate is a layup of plies with fibers in different directions. And each one of these little narrow figures represent a ply, and let's say the ply I'm pointing at can have fibers in the 0-degree direction, pointing upward, and the next ply can have fibers in the 90-degree direction, that is coming out at us. And what we find is there is matrix cracking and delaminations. And delaminations are a separation between, in general, plies with fibers in different directions. And this is what we are going to concentrate on. We're going to concentrate on the separation of the plies, delamination. Delamination is a fundamental mode of failure in laminate composites. The most common sources: material and structural discontinuities, in-service loads, impact. Delaminations tend to occur between plies of different orientation, and as a result of their difficulty, we have a high safety margins are used in composite design, leading to over-design. So if we have accurate fracture toughness values, we can assure composite structural integrity, and this is our aim. So let's see what we're going to talk about. First of all, we're going to talk a little bit about interface fracture mechanics for anisotropic materials. Why anisotropic materials? A ply has fibers, may have fibers, let's say, in one direction, and so therefore it's transversely isotropic. And what we do to get the mechanical and thermal properties is we homogenize the properties, and so we're dealing with anisotropic and homogeneous materials. We carried out testing of Brazilian disc specimens, and we had an interface between two different fiber reinforced plies, and there are 4 different types. We did a 0-90-degree interface. The double slash stands for where the interface or delamination is. It's between the 90-degree ply and the 0-degree ply and the 90-degree ply. And you can think of the 0-degree ply having fibers, let's say, in an X direction, and the 90-degree ply can have fibers, let's say, perpendicular to the slide coming out at us in the Z direction. We also looked at an interface with plies that were aligned plus 45 and minus 45 degrees, and I'll show you a slide later on that will explain it better than just looking at the words. Then we also had an upper ply that had fibers in the 0-degree direction, so it's unidirectional, and the bottom ply was a weave with yarn in the plus 45, minus 45 degree directions. And finally, we had a multi-directional weave with yarn in the 0 degree, 0, 90 degree directions and an interface, and then the ply has yarn in the plus 45, minus 45 degree directions. And so we're going to determine deterministic failure curves and surfaces, as well as statistical failure curves and surfaces, and then we'll draw some conclusions. So the first thing we'd like to do is talk about fracture mechanics for laminates. So we can think of the upper material, material 1, as being a ply, or in this case, we're looking at an infinite half space, but it's the upper ply, has fibers, let's say, in the 0 degree direction, in the x1 direction. And material 2 has fibers coming out of the slide in the x3 direction, perpendicular to the x1, x2 plane. And for that case, we have a complex stress intensity factor. K is equal to K1 plus IK2. I is the square root of minus 1. K1 and K2 are real. And a mode 3 stress intensity factor, K3. And you can notice that the subscript on the mode 3 stress intensity factor is a Roman numeral. And this we reserve for the amplitude of the square root singularity. So the mode 3 deformation has a square root singularity, whereas the in-plane deformation, where we've used Arabic characters for the numbers 1 and 2, the singularity, K, is the amplitude of the square root oscillatory singularity. So I don't have time to go into it, but it's a different singularity, but we can handle it. So we also need the concept of an interface energy release rate, and the interface, I is interface, is the sum of the squares basically of stress intensity factors, K1, K2, and K3. And H1 and H2 are moduli, like Young's modulus kind of quantity, and they depend on the mechanical properties in a much more complicated way. We now have many mechanical properties because our material is anisotropic. And we have two mode mixities or phase angles. In the first case, psi hat is the ratio of the imaginary part. You can think of multiplying K by L to the I epsilon, which is a normalizing factor, and we have the imaginary part of that and the real part of it. So it's like K2 to K1. And phi is a mode mixity, comparing K3 to the sum of the squares of K1 and K2. So we have a mechanical M integral, which we can use to determine the stress intensity factors. These are for applied load. And we obtain K1F, K2F, and K3F, where F stands for force. And then we have a thermal M integral because we have residual curing stresses. And so the stress intensity factors for residual stresses may be found. And that's K1R, K2R, and K3R. We superpose them to get total stress intensity factors. We then substitute in the expression for GI. So we have an interface energy release rate in terms of the total stress intensity factors, and two phase angles in terms of the total stress intensity factors. So here is our specimen. Here is the Brazilian disc specimen. It has a radius of about 40, diameter of about 40 millimeters, and the composite strip is about 13 millimeters in width. And we fill out the specimen with aluminum partial half discs for easy handling to put in the loading machine, the loading device. And you can see here, we have 0 degrees, so we have fibers in this direction, parallel to the delamination, and we have fibers in this layer. There's a number of plies which are coming out at us. The fibers are coming out at us in the 90 degree direction, and we can look between an X1, X3 plane. We have X1 along the delamination, and we have X3 coming out at us in the X3 direction. And we have two we have two different layups. Here we have, this is about 4.5 millimeters, the strip. So we have 4.5 millimeters, 4.5 millimeters, and 4.5 millimeters. So we have a number of plies. Plies are about 0.25 millimeters thick. And here we have a layup where again we have 0.90, but we have 0.5 millimeter layers, and then we have outer stiffening layers. And one would hope that one would obtain the same energy release rate in both cases for the same mode mixity. And indeed that occurs, that we did find that it didn't matter what the layup was as long as the interface was the same. And then here we have a variety of plies and layers. We have plies in the 0-degree direction, the 90-degree direction, the plus 45 and minus 45 degree direction. The delamination is between those two. And so here we have fibers that make an angle of 45 degrees with the X1 axis, and the lower ply makes an angle of minus 45 degrees with respect to the X1 axis. And here's the specimen. You can see it, and you can see the partial discs, and that it's the width or the diameter is 40 millimeters. And we have AS4 carbon fibers in 3502 epoxy matrix with a volume fraction of 0.62, a 62% volume fraction of carbon fibers. And here you can clearly see the thin, in the right figure, you can see the thin 0.5 millimeter thick layers of 0.90. Here's the plus 45, minus 45 degree interface. You cannot see clearly all of the layers, but they're there. And it's the same material that we tested. And so here is our loading frame, which we then put into Instron. Here's our experimental setup. The Instron has a load cell of 25,000 newtons. It's difficult to see the specimen, but with the video microscope, we see the specimen and we have a light source that's lighting it for us. So now we need a failure criterion. We can have a 2D failure criterion or a 3D. So let's start with the 2D since it's simpler. We write GI as in terms of the hatted quantities, the ones that are normalized. And the reason we normalize them is we then can fit the test data to our criterion in a better way. This is a free parameter that we use to fit the data. And previously you saw this as K1 squared plus K2 squared without the hat, but you can show that they're equivalent. And H1, as I said before, is related to mechanical properties, and now you see more distinctly what H1 is. Epsilon is the oscillatory parameter, and D11 is a member of a diagonal member of a 3x3 matrix made out that we determine by the Stroh formalism, and they depend on mechanical properties. And so we can manipulate the expression, the yellow expression, to give us this criterion where we have GIC is equal to G1C average. What is G1C average? It's the average. We take K1 hat of each specimen tested, we calculate it, we square it, and then we take its average to determine G1C bar. And then psi hat is just the in-plane mode mixity, K2 hat to K1 hat, the arctan. And so here is our failure curve. And so how do we use this? We have a structure which has the same material, the same interface, and has a through delamination. We calculate the stress intensity factors. We calculate for the given L hat. We calculate psi. We look, is psi above the criterion, or G? Is GI greater than GIC? Well, if that's the case, then we expect failure. If GIC is below, if GI is below GIC, below the criterion, then we expect that we're in the safe zone. The problem is that when we tested the specimens, we had many in the failure zone, but we also had quite a number in the safe zone. So this motivated us to do a statistical analysis, and that's what I'd like to talk to you about next. So we assume that the GIC bar values form a normal distribution, and this is the probability density, and we can obtain a probability by integrating under the curve from z is minus infinity to a certain specific ZP. So we use the standard normal variant z, and if we want, we say, okay, let's say that P, the probability is 0.1 or 10%. We have a specific ZP, which we look up in tables. It's minus 1.2815. And this tells us that we have a 10% probability of unexpected failure in the safe zone. The turquoise zone is the safe. And so in order to carry this out, we take G1C bar and we decrease it by proportional to its standard deviation. N are the number of samples. So in the case of the two-dimensional analysis, it's the number of specimens that were tested. S is the standard deviation of G1C bar. And then we have this parameter K, which was suggested to us in a experimental statistics from the National Bureau of Standards handbook by Nutrella, which is written here. And so ZP is the standard normal variant for the probability that we choose, and Z gamma is the standard normal variant for the confidence that we chose. And we chose 10% failure and 95% confidence. Here is that. And then we calculate the decreased G1C star, substituted into our criterion, and now we have a new criterion. This is a statistical criterion. So the deterministic criterion in the GIC psi hat plane is given by this equation, where GIC is the average of the K1 hat squared quantities. D, I remind you, comes from mechanical properties. Psi hat is the ratio of K2 to K1. And then we have the statistical failure curve, which is below the deterministic failure curve. So there's only a 10% chance that a data point will be below the curve with a 95% confidence. So let's see how we apply it. Here's our G1C star, which is G1C bar decreased by KS. And so let's take a look, before we go on, at a 3D failure curve. So G is the sum of the squares of the Ks, and of course we have the mechanical properties H1 and H2, and we manipulate the equation in yellow to have the form of our criterion, where all the quantities are defined. G1C bar is the same as before. Psi hat is the ratio between K2 and K1, and phi is the ratio between K3 and the sum of the squares of K1 and K2, the square root of the sum of the squares. And here is our failure surface. So above, we assume that we have failure, and below, we assume that it's safe. And again, we need to do a statistical analysis because we have points below the failure curve, which should be safe. So let's look at some material properties for the 2D problems that we solved, the AS43502 material. Carbon is AS4, 3502 is the epoxy matrix. And if we look at the 090, epsilon is the oscillatory parameter, and it is indeed small. And for plus 45, minus 45, it is very, very small. And there were 24 tests. For plus 45, minus 45, we carried out three-dimensional tests. So at each point each element along the interface, along the delamination front, we had 21 divisions. So we had 26 tests times 21, and so N is 546. And that affects the K value. You can see that when N is 24, K is large, 1.84, but when it's 546, it's 1.38. And so we take our quantity, the average J1C value, which is 26.2 for the 0-90 interface, and we decrease it by K times S, the standard deviation, and we pay a very, very high price. J1C is 5.1, but we now have a handle on the statistics of the problem. And then for the plus 45, minus 45 degree, the G1C star is only about half of the G1C bar. So let's look at the criterion. So the deterministic criterion, the black curve, fits the data very, very well. We use L hat in order to fit the data as best we can to the deterministic failure curve. And you can see in the outliers that it really fits well and convinces, at least it convinces me, that this is a very good criterion for this material and for this specimen. And you can see, of course, that we have experimental data below the deterministic failure curve. G1C bar is 26.2 newtons per meter. That occurs when psi hat is equal to 0. But then we can get a failure curve with a 10% probability of unexpected failure in the safe zone. And here it is. And of course, G1C star is quite small. And we do not have any data points below it. So the next test that we carry out, or the next occasion that we have to use the failure curve, there's only a 10% probability with a 95% confidence that a point will be below this curve. And next, we look at the failure surface for the plus 45 degree, minus 45 degree interface, and we see the data points. This is our failure surface. Phi and psi are defined a bit differently here. It turned out that K2 was the amplitude of the square root singularity, and K1 plus I K3 was the amplitude of the square root oscillatory singularity, but it works just the same. And our G1C average is 92.4, which occurs when psi hat and phi are equal to 0. And I bring your attention on the curve that this is 4 kilonewtons per meter. Let's see what happens with the statistical. In this slide, we have the statistical, it's not a curve, surface. And G1C star has been decreased. It's decreased to 51.9. Before it was 92.6, I believe. And we see many, many more data points above the curve in the failure zone. And in fact, we only have a few data points below the failure curve, and we have to recall that we have 21 data points along the delamination front. So if a few are below the curve and a few are above the curve, we postulate that those that are above the curve in the failure zone will then drag the rest of the delamination front to failure. And now I point out that here we have 3, so we 3 kilonewtons per meter. We see that the surface has been decreased. So next, I would like to just briefly, we have no time to go into the details, briefly show you results for two different interfaces. In the first case, we have fibers in the 0 degree direction, in the x1 degree direction, and we have a weave in the lower material. And it's a balanced plane weave. And this is formed by a wet layup. In addition, we have a delamination between 2 plies. The upper one has yarn in the 0-90 degree directions, and the lower one, material 2, has yarn in the plus 45, minus 45 degree directions. And this was been fabricated by a pre-preg. So we will refer to each. The wet layup is on the left and the pre-preg is on the right. And so here we have the failure criterion for either one of them. And we notice that the difference between this failure criterion and the previous one is that now K1 hat is a function of psi hat. It's not a constant. And so it's a little bit complex, but it leads to these extra lobes in our failure surface. And so below we're in the safe zone like before, and above we're in the failure zone, and this is the deterministic surface. And you can see there are many points below the surface, but there are many points above the failure surface. There's a variety of them. And you're able to see all these points as the surface is rotated about. So for the pre-preg, G1C is equal to 210.2 newtons per meter. That's when psi and phi are 0. And for the wet layup, it's less. It's 114.4 newtons per meter. Now we're looking at the statistical failure curve. And this time, K1 hat is the start quantity, and GIC is also the start quantity, which have been reduced. And here we see the surface, which is the reduced surface, and you can see that there are many, many more points above the surface and very few points below the surface. So that in all the cases, for all the specimens, there were points on the delamination front which were above the surface or completely above the surface for the entire delamination front. And so those are the start quantities. And for the pre-preg, G1C star is 178.7 newtons per millimeter. And for the wet layup, 71.5 newtons per meter. We can summarize for the 4 different laminates that we considered, the 2 for AS4 carbon fibers and the other 2 that had T300 carbon fibers. The first 2 materials are the same. They just have plies in different directions. And we can see for the 0-90 degree interface that G1C bar is 26.2. G1C star is quite a bit smaller, 5.6. For the plus 45, minus 45 degree plies, we have 92.4 for G1C bar, and G1C star is 51.9, which we paid a less of a price for achieving that, and that's because we had many more data points for a 3-dimensional analysis. And now when we look at the 0 degree weave, which is the wet layup, we see that G1C bar is 114.4 and G1C star is 71.5. And finally, for the multi-directional weave, we have 210.2 for G1C bar and 178.4 G1C star. And clearly, the multi-directional pre-preg weave has the superior quality. It's a more expensive to fabricate, but it has superior failure properties. So, in conclusion, we've discussed interface fracture mechanics principles for anisotropic homogeneous material. We've homogenized the plies of the laminate. Delamination toughness tests were carried out on Brazilian specimens. They were both across ply. One had an interface of 0-90. The other had an interface of plus 45, minus 45. Lamination toughness tests were carried out on Brazilian disc tests of multi-directional woven composites, which had superior properties. All specimens were analyzed by means of a conservative and integral to obtain stress intensity factors. 2- and 3-dimensional failure curves and surfaces were presented. All are deterministic. There are also statistical curves and surfaces which predict a 10% probability of unexpected failure with a 95% confidence. The multidirectional prepreg produces the best results. And fatigue delamination propagation tests on beam-type specimens composed of the multidirectional woven materials are also being carried out to prescribe a damage tolerance paradigm. I like to suggest to you to look at the brief book on interface fracture and delaminations in composite materials. And I thank you for listening, and I hope to have questions from you on June 29th when we meet virtually on the internet. Thank you.